In 2022, the James Webb Space Telescope unveiled a universe brimming with mysterious crimson specks, tiny, red, and scattered across the early cosmos. These little red dots appeared in the first billion years after the Big Bang, defying explanation. Compact, luminous, and distant, they were unlike anything astronomers had seen. Their red hues signaled extreme redshift, meaning their light had traveled vast cosmic distances, stretching into infrared wavelengths. But what were they? These little red dots, or LRDs, were not stars. They were too bright, too red, and too numerous in the early universe. Unlike typical galaxies, they lacked extended structure, no spiral arms, no diffuse halos. They appeared as unresolved points of light, glowing fiercely in infrared bands. Yet their sheer abundance at high redshift, Seg 4-7, suggested they played a crucial role in cosmic evolution. But without visible structure, their nature remained a mystery. Enter Fabio Pacucci, an Italian-American astrophysicist at the Center for Astrophysics Harvard and Smithsonian. Born in Taranto, Italy in 1988, Pacucci had spent years studying the formation of the first black holes. His doctoral work at Scuola Normale Superiore in Pisa focused on black hole seeds, primordial objects that could collapse directly from gas clouds in the early universe, bypassing stellar evolution. Now, he turned his attention to the little red dots. Pacucci had already pioneered tools like GEMS, growth of early massive seeds, to model how early black holes might appear across wavelengths. Using Hubble, Chandra, and Spitzer data, he had identified candidate direct collapse black holes. Now, with JWST's unprecedented sensitivity in the infrared, he saw a new opportunity. Could the little red dots be these elusive primordial black holes caught in the act of forming? The challenge was that little red dots didn't behave like typical active galactic nuclei. They were faint in X-rays, unexpected for objects with intense accretion. They also vanished at lower redshifts, suggesting they were transient. If they were black holes, why weren't they shining brightly in high-energy bands? And if they were galaxies, why couldn't telescopes see their stars? Meanwhile, a team led by Pierluigi Rinaldi of the University of Arizona's Stewart Observatory was studying a galaxy nicknamed the Saguaro, YZJ 2036 35.56 plus 600 21,424.2. At redshift 2, it existed 3.3 billion years after the Big Bang, much later than the earliest LRDs. But its core, a compact bright red source, looks strikingly similar to the distant dots. Could this be a modern analog? The Saguaro was special. Unlike distant LRDs, it was close enough for JWST and Hubble to resolve its full structure. There, surrounding the red core, were spiral arms filled with stars and dust. The core itself resembled an active galactic nucleus, obscured by dust and glowing in infrared. But when viewed from afar, only the bright red center would be visible, the outer arms too faint to detect. Rinaldi's team simulated how the Saguaro would appear at higher redshift. As the galaxy receded, its spiral structure vanished. Only the luminous red nucleus remained, indistinguishable from a little red dot. This suggested a radical idea. LRDs aren't a separate class of objects, they're galaxies in disguise, hidden by distance and observational limits. George Reek of the University of Arizona noted, "Everything created in the early universe must evolve into something around us. We have had little idea of what LRDs become, but these results finally show us how to find their progeny." The Saguaro offered a missing link, a nearby example of what distant LRDs might evolve into. The discovery built on earlier work from Spitzer, which had hinted at a population of dust-obscured compact galaxies at lower redshift. Now, with JWST's resolution and Hubble's optical data, astronomers could connect the dots, literally. The Saguaro was a prototypical LRD, as Pacucci described it, offering a rare glimpse into their evolutionary pathway. But Pacucci didn't stop there. He proposed a deeper explanation. What if little red dots weren't just obscured galaxies, but hosted overmassive black holes? In a 2023 study, he showed that LRDs violate the local black hole stellar mass relation by over 3 sigma, meaning their black holes are too massive for their host galaxies. This suggested a different origin, direct collapse. Direct collapse black holes form when massive gas clouds collapse directly into black holes, weighing 1 to 10 million solar masses, bypassing stars entirely. These objects could grow rapidly in the early universe, accreting matter at rates just above the Eddington limit. Pacucci's simulations showed that such accretion could explain the infrared brightness and X-ray faintness of LRDs. In a 2024 study with Ramesh Narayan, Pacucci demonstrated that mildly super-Eddington accretion onto slowly spinning black holes could suppress X-ray emission. The infalling material forms a thick, radiatively inefficient disk, trapping high-energy photons. This explains why LRDs shine brightly in infrared but remain faint in X-rays, despite intense accretion. Pacucci and Avilob further proposed that LRDs arise in low-spin dark matter halos, regions where gas can collapse more efficiently. These halos, predicted by cosmological structure formation models, could favor direct collapse over star formation. The morphology of LRDs, then, is tied to the earliest conditions of the universe. In his latest work, Pacucci claims that all observational properties of LRDs, luminosity, color, size, redshift distribution, and X-ray weakness, can be explained by direct collapse black holes accreting mildly above the Eddington limit. This represents the first unified model for LRDs, linking their appearance to fundamental physics. This model challenges the idea that all supermassive black holes originate from stellar remnants. Instead, some may have formed directly from primordial gas, seeds that grew rapidly in the universe's infancy. If true, it reshapes our understanding of cosmic origins, suggesting that the first black holes were not small, but already massive. Yet Rinaldi's team emphasized another factor: observational bias. At high redshift, even large galaxies appear tiny. Their outer stars and spiral arms fall below detection thresholds. Only the brightest, most compact regions, like dusty active cores, remain visible. Thus, LRDs may not be intrinsically different, but simply what we can see at extreme distances. This doesn't contradict Pacucci's model, it complements it. The Saguaro shows that galaxies with bright red cores exist at lower redshift, but in the early universe, such cores may be powered by direct collapsed black holes, making them both obscured and intrinsically different from later AGNs. The truth may lie in both physics and perception. The sharp decline in LRD numbers at lower redshift supports this. As the universe ages, black holes grow more efficiently, galaxies become less obscured, and accretion stabilizes. The red dot phase may be a brief, intense epoch, when black holes outshine their hosts, hidden in dust and distance. JWST's ability to peer into the infrared has revealed this transient phase, but without nearby analogs like the Saguaro, interpreting these signals would remain guesswork. The Saguaro bridges the gap, showing that what looks like a dot in the distant universe may be a full galaxy up close. So, what are the little red dots? They may not be a single population. Some could be obscured galaxies like the Saguaro, bright cores hidden by dust and distance. Others may be true direct collapse, black holes born from primordial gas and low-spin halos. Both explanations are supported by data, and both reshape our view of cosmic evolution. Pacucci's work suggests that direct collapse black holes could explain the most extreme LRDs, those with overmassive black holes and faint X-ray emission. These would represent a new class of objects, challenging the standard model of black hole formation. If confirmed, it means the first supermassive black holes didn't start small, they started big. Meanwhile, the Saguaro shows that observational limits play a key role. What we see depends on distance, resolution, and wavelength. The dots may not be dots at all, just galaxies whose outer light has been lost to cosmic expansion. This echoes a long-standing lesson in astronomy: appearances can deceive. The convergence of these ideas, Pacucci's theoretical models and Rinaldi's observational analog, marks a turning point. For the first time, astronomers have both a physical mechanism and a cosmic precedent for the little red dots. They are not just anomalies, they are windows into the universe's earliest phases. These objects may represent a critical phase in galaxy evolution, when black holes ignite, dust shrouds starlight, and the universe undergoes rapid transformation. They could be the seeds of today's quasars and elliptical galaxies, caught in the act of forming. Pacucci continues to lead this research, using JWST data and simulations to test his models. His work, published in AppJ and submitted studies, is shaping the field. With over 200 scientific papers and a passion for science communication, he bridges discovery and public understanding. He has collaborated with TED since 2018, creating animations on black holes and cosmic evolution. His videos, translated into over 25 languages, bring complex ideas to millions. For Pacucci, science is not just discovery, it's sharing the wonder of the universe. The mystery of the little red dots is not fully solved, but it is unfolding. JWST has opened a new window on the early universe, revealing objects that challenge existing models. Whether they are obscured galaxies or primordial black holes, they force us to rethink how structure formed in the cosmos. Future observations will test these ideas. Upcoming missions like NASA's Habitable Worlds Observatory and the AXIS X-ray mission will probe deeper into the X-ray faintness of LRDs. Pacucci, as co-chair of NASA's X-ray Science Interest Group, is helping shape these efforts. Meanwhile, simulations will refine our understanding of direct collapse. Can gas really collapse into million solar mass black holes without fragmenting into stars? Radiation hydrodynamic models suggest yes, under the right conditions of low spin and high gas density. The Saguaro galaxy remains a key reference point. By studying more analogs at intermediate redshift, astronomers can map the life cycle of LRDs. Are they all destined to become quiescent galaxies? Or do some remain active, evolving into today's brightest quasars? One thing is clear, the little red dots are not just dots, they are cosmic signposts, marking a turbulent, formative era in the universe's history. They remind us that the early cosmos was not a quieter version of today, but a place of extremes, where physics operated at its limits. And with every new JWST image, we come closer to understanding our origins. The red dots may be small, but their implications are vast. They challenge us to see beyond appearances, to look past the dot and into the hidden galaxies and primordial black holes that shape the universe we inhabit.